This boxing match will be my apprentice's biggest challenge, but I think he's ready for it.
Used to work at Five Below, but now I keep that Five Below. Them hearts cold, wood ain't melt. Robert Frost or does it explode? Them boys suck, to each his own. They tried to slide, epic poem. So if it's smoke.
And your defending champ, Exterminator and his coach Bacon. Defending champs, 8 KOs, 8 knockouts, never lost a match in his life. And time for the challenger, fresh and healthy produce. What? Where's his coach? So, Fresh Produce, how you feeling tonight?
I'm feeling pretty great. My coach is still late though, still waiting on him.
Yeah, where is your coach, by the way?
I have no clue. Maybe he's just. What are you doing here, sir?
Your coach got ran over 15 times. There's nothing left.
What do you mean? What do you mean?
We didn't even pick it up.
No. Oh, I have to win this fight for my coach.
Rock on, brother. So, Exterminator, how you feeling tonight?
I feel great.
How do you feel that all 6 of your wins have been knockouts?
They're too easy. They're too easy. I want a challenge.
How do you feel being the undisputed champ that this current is trying to take a run of a mill for your money?
I feel great. I'm gonna kill him. I'm gonna kill that man.
What's the deal, man? You've been through like 8 coaches.
They'll just really make me angry.
Let's see who wins. Good luck, Exterminator. And now for the face-off.
I'm about to apply non-linear velocity to your head.
I'm gonna give you an initial velocity in the Y direction, Buster.
Oh yeah? Well, I'm gonna apply a force upon a long time to your face.
I'm gonna use the work energy theorem to change the amount of kinetic energy you have.
Oh, that's it. That's it. That's it. That's it.
Hold me back. You're dead.
Touch gloves, touch gloves.
Come here.
Round 1.
Don't make me apply harmonic motion to your brain. That's it. I'm gonna turn this chemical energy into kinetic energy.
Oh, we're going after it.
Transfer heat to his face!
Uh-oh, another coach that just don't know physics.
Heat?
No.
Not real!
Wait.
Excellent, Transformer.
I got heat horribly wrong. You're not feeling heat. Heat is the transfer of thermal energy between 2 objects. What you're feeling is not heat. You're feeling an object that has a higher thermal temperature.
And Mr. Willard killed his 6th coach. Anyways.
I have to stop you! Force on the edge! Torque! Momentum!
By the way, I killed your teacher.
You're a monster!
I'm not a monster. I'm physics. AP Physics!
Master, where am I?
We're inside of your mind.
How is that even possible?
You wouldn't understand. You are just a physics beginner, my friend. Just even before the fight, you cited incorrect physics knowledge.
I'm about to apply non-linear velocity to your head. Oh yeah? Well, I'm gonna apply a force upon a long time to your face.
How would you know? You weren't even there.
I was there, watching over you. Our time here is short, my Padawan. Mr. Willard has grown too powerful. His knowledge of physics is too great. I must teach you the move.
I thought you swore to never teach that to another student.
I did, but Mr. Willard must be knocked off this evil path that he's on. Come, Padawan. We have little time and much to learn.
2, 3.
No wonder he got knocked out.
There are several ways in which someone can get knocked out, and we don't know which is the most prevalent. A force to the face in the form of a punch over a period of time applies an impulse to the brain, changing its momentum by giving it a velocity. Once moving, your brain oscillates back and forth in harmonic motion by bouncing off the walls of the skull. These impacts kill brain cells, causing your consciousness to fade away temporarily from the damage. A punch to the jaw can be so effective because the force along radius can cause a torque that makes your brain rotate, increasing potential damage. Forces on the head can also disturb blood pressure in the brain. Keeping a steady blood pressure is vital for the brain, so any change can cause parts to stop working, leading to lost consciousness. Another theory is that impacts to the brainstem can cause a rush of electrical signals through the neurons that the brain cannot process, causing it to shut down as a defense mechanism.
Seven, 8, 9, and the current gets back up.
Perhaps I underestimated my opponent. He is stronger than most.
Finish this clean, boys. You should have told me about my coach. You increased my potential energy tenfold. Just wait till my fist magnetically attracts your face to it. You might be AP Physics, but I'm taking the Physics C test. It had to be done. You are a monster.
That's alright, son. I ain't seen a move like that since now.
You see, if we examine Carrot's punches, we see that he punched in a circle instead of a straight line punch. So now we have to use our torque equations instead of our normal straight line force equations that we can use if he punched in a straight line. Torque on the y is exceptionally easy as angular acceleration is 0, thus our torque is 0. In the x direction, it's significantly harder. The first problem we run into is Carrot is not a shape that we can easily find inertia for, so let's turn him into one. As a rod is a great choice as the center of mass is still its midpoint and it's still what he rotates around, and it kind of resembles a human. However, this leads us into a very new and huge problem, his change in density. As we smush Carrot into a rod, some places, for example his head, have more mass stuffed into a rod than something like his outstretched arm. And this is bad because our density is related to our mass divided by our volume. So as we stuff more mass into certain parts of the rod, we are changing the density. This is bad because we can no longer use our uniform density like we do for every other problem we'll ever do in this class, because his density is changing. Here's a visual representation of what I'm talking about. Each part of his body has a different amount of mass and thus different densities when it's stuffed into the rod. And due to all the volume being the same, it's a constant and unnecessary and will be cancelled out while doing the math. Now for a better chart. Neri Christianon, Journal of Engineering Science and Technology, explains and splits up how much of our mass is divided to each part of our bodies. This is useful because we can use his information to see how much mass each section of Carrot will have by adding up what parts of his body make up that section, as you see we've done on this slide. We also need to measure all of Carrot's parts, as distance or radius is still required to find inertia. Then we simply need to build a proper graph. Using some elementary calculus and the data we already have, which I'm not allowed to go into because of a certain someone who hasn't taken Calc AB, we'll end up with this chart. With this, we can now find moment of inertia, which once again I'm not allowed to go into and prove, so we'll go with our research stint. And we need to use the polar moment of inertia as we are turning Carrot and spinning him to produce a torque. We cannot use simply the x or y inertia because that's only the inertia on that plane. So, plugging into the equation, r is the distance from the origin, and we'll use x squared as y squared as is equivalent to r squared, and our chart is already in terms of x and y. And our density function, we still do not know. However, using our system of equations from the chart, we can split up our density functions into multiple functions we do know and can just look at from the chart. And using those functions, we can find our overall moment of inertia. We need to still leave k in as it's proportional, as density and mass are still proportional, but not necessarily a factor of 1. Once again, I can't really teach you my math, but you're going to have to trust me on this one. Stealing that k value from the rod of 1/12 as we turned Carrot into a rod, we can find our final inertia of being 51.42 kilograms times meters squared. Now on to acceleration. Starting with time, we use our super slow motion, ultra hyperspeed, ultrasonic boom camera that told us that Carrot only took 1.6 seconds to spin. Using our other variables as angular velocity initial, which was 0 as he started from rest, 2 pi for our theta as he only spun in one circle, and our time from our last slide, we're all familiar with how to find our angular acceleration from this point, which comes out to 33.771 radius over second squared. Now time for the force of that punch. We can conclude that the torque the punch had was 1,722 Newton meters, and he hit eggs, of course, with a force of 2,002 newtons. This is well beyond the average human punch at only 500 to 700 newtons, putting Carrot closer to the level of an amateur boxer who punches around 2,500 newtons to Carrot's 2,000, data from Richard Ray, who is both a martial artist and a scientist. It ain't no wonder you lost, son. You just got out physicsed.
Force equals mass times acceleration.